Hello everyone, my name is Dr. Dror Malka. I'm from Holon Institute of Technology, and today I'm going to talk how to design a special coupler, special multi-mode interference coupler. So for starting, let's share my presentation. Screen. Tile screen. Share. Everything is working perfect. Okay, so everybody hear me? Okay, so let's do a full presentation. Okay, as I said, my name is Dror Malka from Holon Institute of Technology from Israel, hello from Tel Aviv. And today we're going to talk about how we can design a special photonic design, which is very special product, especially for the field of AI and silicon photonics and data center. So the topic is AI, intelligent enhanced design of compact 4-channel based on silicon nitride, multi-mode interference, wavelength division multiplexer for energy efficiency or band data transmissions. So I hope you will enjoy the movie, and of course this is the main event today. Okay, so let's start. What we're going to talk about, what is optical multiplexer and the multiplexer devices, and why they are so important to increase bit rate in data center application and also in optical communication, and what is the relation to use in AI, the motivation of the work, the new silicon nitride MMI multiplexer devices. We're going to review about what is multimode interference waveguide and all the theory why we use this coupler and not other coupler like directed coupler or other stuff. We're going to review my previously published work, 123 silicon angle MMI combiner design, and we're going to explain why I use angle shape. Also 4-to-1 wavelength multiplexer design, some equation and key parameter. We're going to see the problem with the mathematical and the analytic solutions. We're going to overview the strip waveguide optimization of the silicon nitride, and we're going to see all the results that done by Synopsys company, by the RSOF CAD software simulation, and the profile mode of the TE fundamental mode solution, the tolerance and the optimization for the fabrication requirement, the results of the intensity, of course the back reflection, which is a special aspect that usually science or not cannot calculate it. Only company can do it, and I will explain why it's so important for company to do that. Also the optical spectrum, comparison between this work and other state of the art, and in that I'm going to conclude my talk. So let's start. Okay, let's start. Why optical multiplexer and demultiplexer device are a key component in wavelength division multiplexing technology. This is because there are many use of optical data, and as we can see, everybody wants more and more speed and more storage. So we have two methods to increase the transceiver. What usually AMD company and NVIDIA company doing is every time they want to take their single mode fiber transceiver and make more data. Now you can find in their website, you can find 400 gigabit per second. And of course, if we want to go to 800 or 1.66 terabit bit rate, we have to increase the bit rate. And this can be done only by two ways or maybe three ways. Of course, if you have a speed rate of modulation, so you don't need this method, but this is very difficult because usually they are using Mach-Zehnder modulation, which is limited to maybe 100 or 200 gigabit per second, and 200 it's crazy speed for this device because there is many problematic with this design. So they use a wavelength division multiplex, and if you multiplication 2 channels, I multiplication the speed by 2, and if I multiplication 4 channels, I multiplication by 4, and this is the idea. Another method is, of course, to use a special modulation method. For example, if I use PAM4, I can transmit for one symbol 2 bit, and then I can multiplication the speed by 2. So if I combine this method and my method, maybe I can increase the speed of light by 8. But of course, there is always trade-off, and we're going to talk about later about the trade-off from engineering view. What is the price or the penalty that I'm going to pay for increasing the bit rate? So the application of the device, of course, is for wavelength diffusion multiplexing or dense wavelength diffusion multiplexing, which is more suitable for the C-band, which is between 1,530 nanometer to 1,570 nanometers. Also using for data center, which is in the O-band or the optical communication. Also, we're going to increase the data bit rate, and of course for photonic chip. Okay, let's continue the motivation. Of course, the motivation is to increase the bit rate, but we have problem with this because how we can succeed to do it. So I explain how we can, for example, how we can go to 800 gigabit per second if I use 4 channels and PAM4 together. So multiplication by 4 and 2, so we get 8, and I need the modulation for 100 gigabit per second. So this is possible. But the motivation today is that we have a problem. Usually we have 2 problems. The challenge is the size of the large footprint for special design if you want to do it, because if I want to multiplexing many channels, it will be a challenge, and the trade-off going to be I have to increase my chip, my footprint, and then if I am increasing the footprint is more power meaning that I'm losing a lot of money. So basically the main motivation of this work is to reduce the techniques and do it without using a many couplers. So today you can use a cascade of couplers to increase the bitrate, but the penalty is it will take you millimeter space from the footprint. So this is a big challenge. Also another problem, of course, is the back reflections that we can deal with this by replacing the silicon to silicon nitride, and also integrated tapers to reduce the back reflections, which is very problematic because if I have a strong back reflection in my system, it will damage the signal. You will not get the communication, and of course it will affect the speed. Okay, to respond to this challenge, we propose a new method for a 4-channel silicon nitride MMI coupler with only a single coupler, which is amazing. I will explain later why it is amazing, because there is no solution for this. I will explain why from an analytic view, but we did it numerically by using the AI machine, and I will explain why later. So we use a new silicon nitride multiplexer, which is a new approach for design a multiplexer based on silicon nitride strip. Why we use a strip waveguide and not special waveguide like rib or slot waveguide? Because we want something very simple that it will be easy to fabricate it. So it's proposed for solving the high demand for high speed ability. Of course, our specific aim is to support C-band, O-band range. O-band range, I didn't say it, but by the way, it's between 1,260 nanometer to 1,360 nanometer, which is the basic band that we are using for data center applications. And C-band is more suitable for long distance of optical communication. Of course, low cost, we want low power consumptions. We want small footprint, and we want, of course, good flexibility for the fabrication error, which is very important. Of course, if we want to fabricate it in a good fab, like we have in Taiwan Semiconductor Manufacturing, which is the best fab in the world. So let's continue. So the multi-mode interference waveguide. Let's talk about what's so special about this device. Well, basically, this device acts like a mirror. It's like what you transmit the light inside. If we can see here, let's see. Let's see how I can do. Let's see. Wait. I have to see how I can do a pointer. Maybe here. Here. Perfect. I solved it. Now we have the laser pointer. So here we can see the laser pointer. We can see that light is transmitted here. For example, here we design a very simple coupler splitter 1 to 2. And we can see the same energy multiplicate again and again. It's like going to the park when you have a lot of mirror and you see yourself again and again, but with different energy, because the long that we propagate it, we have more losing energy. So this is the profile of this device. So in a multi-mode waveguide, an input field profile is duplicated in a single and multiple image at periodic interval along the propagation axis. This is what I show you. And of course, we fabricated the device, which is very easy to fabricate, and it's very robust for fabrication alignment, which is very necessary for accuracy, especially to avoid fabrication error. So let's continue. So in the past, we designed a combiner based on silicon. But the problem with silicon is that the back reflection with the cover, with silicon with silica, it's too much for commercial laser. We don't want to hire the cost of the system, so we will not use a special laser. We want to use a commercial laser, and in commercial laser, usually the back reflection is limited to 35 dB. So to reduce this, we use a special structure, more complex. We use here the angle. Here we can see the angle. We can see the length of the angle, and we create here the angle. So we calculated and optimized this using the FDT simulation, finite difference time domains simulation. Here we can see the setup of the simulation, and to do it, it's very complicated to calculate the back reflection, because we have to launch the field in the direct direction and also in the reverse direction. So if you do the simulation, you have to increase the time at least by 2.5. It's enough, I think. This is what I'm usually advised to my student to do. And we put a monitor in the beginning to collect the light coming back to see the effect of the improving of the back reflection. As we can see here, the results. A perfect improving of the back reflection, but of course there is penalty. If the intensity here was 87%, we reduce it to 82. There is always penalty in engineering. You can improve one item and you will lose another item, but in here it's very crucial because it's very critical aspect, because back reflection is the most critical aspect in a communication system and in data center transceiver rooms, because if not, will not function well. So I prefer less energy but more functionality. The functionality is much more important for us. This is why usually scientifics are not calculated this aspect, because it's very difficult to do it. You need a very powerful computer, and later we will talk about the process of the computer and why we need AI also. Okay, now we're going to talk about our design. So our design is very simple. We take a strip silicon nitride, as we can see. Here is the input of the 4 tapers, and we use taper, of course, for 2 reasons. One, to reduce the back reflections, and the secondly reason is it's very important to keep the single mode, the field of the single mode in the same solution. So if you use a taper, the mode is not changing. So it's very important to do that. And what is the benefit of our design? Our design is only one coupler, and later I will prove that is from theoretical view, it's not possible to demultiplex more than two channels. You cannot multiplex in more than 2 channels in one coupler, but we succeed to do it more using the AI, and I will explain this later. And we have, of course, the output taper. So let's continue. So the green color, of course, is represent the silicon nitride materials, and the white color represent the cover material, which is, of course, is silica, which is basically what we are using when we are doing fabrications. Okay, so let's review the equations. So the first equation shows the bit length, how it changes. And what is the bit length in the MMI? The bit length represent, and in engineering way, it's how much energy is transferred from one direction to the other direction when you propagate over the axis. So this is very important to calculate it, and we can see that is affected by the wavelet, of course. So if we change the wavelet, all the optical path in the MMI will change. Also, of course, the width, the effective width is affecting, and also, of course, the solution of the mode. Effective index is a parameter that reflects the solution of the mode. And of course, also the mode is controlled here by sigma. If we have a T or TM solution, it's differently sized. And here we can see the explain that how we can demultiplex or multiplex more than one wavelet using MMI coupler. So we can do it. We can calculate it here, and we can solve it using algorithm, or can use a CNN model, or we can use a AI model to solve it very, very quickly. But the problem is that it only will affect one coupler, only will be analytic solution can be very approximately exist for only for two wavelengths. But in our case, we are going to do it for four wavelengths. How it's possible? It's not possible, by the way. I try to solve this equation using the MATLAB, using the Python. I have no solution, again and again, no solution. Then I write a model for using CNN and AI to extend the data coming from the simulation from the RSoft. And then I didn't say that I want a perfect solution. I don't want 85%. 80%, 85% is an excellent solution, usually from engineering view. But I reduced it to 80%, and in 80% I was very close to solution, and then I reduce it more to 70%, and I found solution in 70%. So I'm losing much more from the energy when I do the multiplexing, but I have a solution. So this is the price I'm going to pay, but I'm going to reduce the size of the footprint by 100 size. It's crazy. So this is the benefit. So if I want to compensate that, I can put an amplifier that can amplify, or I can use a higher laser or something like that. So I can do a combiner. So I have a solution for this, but if I combine my solution, the footprint will be much more minimized size. So this is the novelty of this research. Okay, after I explain the novelty and how I use the AI to get it, now I use, of course, we use also the AI to get all the tolerance. Also, we can use the MATLAB or Python to understand all the data. So here we do, of course, the fabrication, which is very important. And of course, the thickness of the silicon nitride is 410 nanometer. And of course, it's maintained 80% for any increase in the height up. So it's enough for us, because usually Taiwan Semiconductor can handle until 20 nanometer error. So it's good results. Here we can see the solution of the strip for one strip MMI waveguide in the silicon nitride. We can see very strong confinement inside the strip. And here we can see the input for the four wavelength. It's very important to understand that each wavelength is differently. It's not the same. Everybody belong, of course, we designed this design to be suitable to the O band. So the strong confinement can be noticed in the red color. And of course, this is also explained, so we can continue. And we continue to do the tolerance range using the RSoft beam propagation method. We use also full vectorial beam propagation method. And we use, of course, also MATLAB script and Python script combined with our model and AI also to boost to find a better solution, more accuracy, to find the solution of the MMI that's suitable to 4 wavelength, to do multiplex 4 wavelength. So this is the optimal of the width of the MMI, which is a lot of tolerance range. It's 11.2 micrometers, as we can see here. And we can see we have a perfect tolerance range, above than 100 nanometer. It's crazy. It's robust device. So we have no problem to fabricate it, and the fabrication error will be very low. So the tolerance is between 600 nanometer, which is crazy. Also, the width of the MMI coupler, we have a good tolerance there, with more than 80% of the normalized power. So we have very low losses from the fabrication error point. So this is a great challenge, and we get a great solution in this case. And here we can see the results of the beam propagation method. And what is the difference? That we change the wavelength. So here is the wavelength 1310 nanometer, which is in port 1. We launch it here, and we can see that we didn't get all the energy. We have losses here and here, of course, because I designed this that it will be suitable to 70% of the energy, something like that. So we have losses 1.24 dB. This is the losses energy. So it's okay from my point of view to lose this energy. Also here we can see that we only changed 20 nanometers in port 0, which means that the difference between the wavelengths are very, very short. And of course, all the wavelengths are the most important wavelength for the O band. And we can see here also we have the scattering of the losses, but most of the energy going into the output, which we have more losses in this case, 1.6 dB. And also in port 3, the same story, and we have more losses, 1.67. And again, we change for 40 nanometer between port 3 and port 4, and we have less losses, 1.3 dB. Excellent results from my point of view. So we can continue. And then, of course, we combine the overall loss of the O band. And as I expected, it was very close to the solution that I get from the AI, which solve the hard all the equations, that all the possibility of all the wavelength. It's very difficult to do it, and we use a very powerful computer to analyze and to find the right geometrical parameter of the MMI, which include all the geometrical parameter. So the total loss, it's only 30% of the energy, which is, I can live with this, it's no problem. And of course, we did the simulation of the back reflection, which is very important. In our case, this is why we use silicon nitride and not using silicon. Many people ask me all the time, why you are not using silicon? Why you always choose the silicon nitride? And then I explain to them, hey, this is multiplexer. It's very close to the laser system. It's not in the receiver, it's in the transmitter. Because it's in the transmitter, you have in the fourth step, you have the laser, and then you have the coupling machine. You have to put a taper to coupling and match the mode between the laser mode to the taper mode. And then you have the multiplexer. So back reflection, it's very important to reduce it, especially when the component is very close to the laser. Because if it's not close, it's okay, because many power losses will become in overall all the optical path. So the result here, we can see the same trick. We use 4 monitors to calculate the overall back reflection coming from the MMI. This is the problem of the self-image effect in the MMI, as I explained, by multiplication the mirror again and again. The problem is that it's going to direct variation and also in the reverse direct of the light. So the same propagation we got here. So it's in 2 directions. It's a very linear system. Okay, so we can see in the red light the monitor. So we can see here the results. We have very low back reflection for all the 4 wavelengths, as we expected, and this is very good for us. And of course, the optimal size was very, very low, 8 nanometer, to ensure a satisfactory of the conversion of the results. I will explain. If I want to do the solution of this more speed, because it's 20 micrometer, it's very difficult to do it. But today we have very powerful computer. In the past, when I remember when I was a student, I cannot only solve 2 microns in using FDTT solver, but today we can solve not only micrometer size, we can go to millimeter, because the computer today, and I'm talking about, of course, server computer, which is very high powerful, we can do it today. And then we can calculate it, this simulation, which we cannot measure before 5 or 6 years, something like that. Okay, so let's continue. Also, we can see the optical spectrum. We can see a good isolation between the 4 wavelengths, which is very important. And we achieve, of course, transmission efficiency very high. Everybody are basically above 70% to wavelength and less than 70%, but basically if we take all the 4 wavelength is around 70%, which is good for us. The spectrum also reveal excellent channel isolation, attention to the device design that ensure a significant spectral separation between the 2 channels, which are close neighboring channels with 20 nanometer channel spacing, as I explained in the results. So now we can continue and we can do the comparisons. So let's see the comparison. Let's start with the footprint. In our design, the footprint is very small. Everybody do it, but everybody do it very high. Compared to this, this is the list that I found in the papers. So this, if I reduce this and this, is 20 multiplication. It's crazy. And here it's also more than 20. So this is the benefit of our design. We use only one number of coupler and the other using much more. Maybe they have better losses. Yes, here, and here we are not the best. We are not the best in power losses. In back reflection, of course, this work, I publish it, and this I publish. Nobody mention it. Why? Because most of the scientific using the academic cannot resolve this parameter. And the spectrum also, most of them in O-band or C-band, as we can see. So we can see the benefit of this work comparing to other work, and we can see the novelty. And of course, this work also published, I think I published it in Nanomaterials journal. And now I want to conclude my talk. So this study introduced an innovation for channel multiplexer design for the O-band spectrum, utilization multimode interference coupler technology with silicon nitride strip waveguide. This study unveiled the trade-off between power efficiency and compact footprint area, demonstrating the effectiveness of using only one coupler, MMI coupler unit for multiplexing 4 channels. Of course, the important suggest device design can be easily produced using correct fabrication technique. Of course, you have it in many companies, but I recommend Taiwan Semiconductor. Thanks to the favorable tolerance range of 350 nanometers, so 300 nanometers for MMI coupler width and length. Also, the findings suggest that such device hold a promise for data center application, of course, for increasing the bitrate, particularly for enhancing data bitrate in transceiver data center chips. In our scenario, our device can multiplication the bitrate by 4 and combine by the PAM4 modulation, as I explained, because every symbol have 2 bits, it's multiplication by 2. So 4 multiplication by 2, it's 8. So the factor of 8. So this is very crazy. So I want to end my talk. I want to thank for your attention. If you have questions, of course, everybody are welcome to ask. And hope you are having a good